Hello and welcome. Hi. So today we are talking about vectors and calculus. Vectors, really quickly as a reminder to everybody, are just line segments with the direction. So the two things that a vector has that we are concerned about are the length of that line segment, also known as the magnitude of the vector, and the direction of the vector. So magnitude and direction. If you have the magnitude and the direction, that's all that you need. So if you have something that looks like that right there, this is a vector. If I were to take this and copy it or clone it, so I now have this guy, and I put it over here, so it's in a different location, or up there, or anywhere. So if I call this vector u and this vector v, vector u is exactly equal to vector v, because the two components of that vector, which are magnitude and direction, are exactly the same. Okay? Now, you could talk about magnitude as, the length of the vector, but really what that represents, can vary a little bit. For forces, we talk about, stop talking please. For forces, it's about the strength of the force, right? Is the force strong with this one? Meaning, right? If we had, myself and who's weak? Who's weak? Wade, come on up. Okay, so if I were to take this and move it in this angle right here, with the force that I have, I'm going to push it and it's going to go, and even the resistance that is there from like the friction or whatever else, right now the resistance is that one of these brakes is on. Okay, good. So, right, even with all that, I'm able to push it in this direction with a certain amount of force. Whereas Wado over here, come on over here, bud, he's going to push it that way, but he's pretty weak, obviously. And so he could, go ahead. He's still pushing it that way, but with less force, meaning for any forces counteracting or acting against it, against the force that he's pushing at, that's going to affect it in a way that it's not going to go as far or as fast, or it's not as powerful, right? So if you have someone very strong and someone very weak, and we're both pushing on this thing, let's say that I'm pushing, well, let's first completely oppose one another. So he's pushing in this way, and I'm pushing in this way. Ready, and go. What's going to happen is it's going to go this way because they're completely opposite directions, yet the force that I'm applying is greater than the force that he's applying. Right? So it's going to go in exactly that direction. If we are, and this is like your tugboat example, they would be pulling, but we're now pushing. If he pushes this way, so from, let's say that this is exactly straight ahead of this thing that we have, he's going to be pushing at, let's say, from this, maybe 30 degrees this way, and I'm pushing it 30 degrees this way. But I'm pushing with more force. The path of it is going to go somewhere over here, right? Because somebody might say, well, wouldn't they counteract when you're moving it exactly forward? Only if the magnitudes of the forces are exactly the same would that make it go exactly straight. Does that make sense? But if I'm pushing with more force than he's pushing, then I'm taking over, right? And it's going more in that direction. Thanks, Wade. Next time for an exam, I'll make you be the tough one. But that's what we got going on. And if we had another vector, right, and let's just make this guy right there, and I would call this vector W. Well, the resultant vector, and again, this is in calculus, right? This is pre-calculus stuff. So the resultant vector of vector U and vector W, you could align them. So this is called the initial point of the vector, and this is the terminal point of the vector. But oftentimes it's just called like the tail and the head, where the head is just where the arrowhead is. And so if you go tail to head, then the resultant vector is going to be, let's make it a different color, like red. This is your resultant vector right there. So this represents U plus W. This is the resultant vector. Okay. Now, this is good to know. This will not be on the AP exam or any one of my tests. It's just like a quick review. Now I'm going to start getting into what you need to know. Okay? So, for vectors, we're going to talk about the position vector, the velocity vector, and the acceleration vector, and then also talk about speed of a particle based on, let's say, the velocity vector. So, the way that we represent vectors is, so for the position vector, it's going to look like this. X of t, comma, y of t. In those little, I don't know what you would call those. Yeah, kind of like sideways carrots, right? What?
Oh, the carrot, like the...
Yeah, this is called a carrot. Like,
That does not look like a carrot.
no.
Yeah.
Anyway, whatever you want to call it. So, this is the position vector, x of t, comma, y of t. Now, vectors kind of brings together what we've talked about in terms of parametric. You see how it has x of t and y of t, which is just like what we've seen with parametric. And what we were talking about with polar. Because with polar, again, similar to vectors, it's all about magnitude, or the distance away from the pole, and then the angle, right? Isn't that what polar is? Dealing with the distance away and then the angle? So that's how vectors, just in general, relate to polar, because both of those deal with a distance or length and an angle measurement, right? Polar is a point, whereas vectors are the actual, like, directed line segment, right? So this is the position vector. The velocity vector is just x prime of t, comma, y prime of t. And the acceleration vector is exactly what you think. X double prime of t, comma, y double prime of t. Now, I'm using the whole prime notation here. If you wanted to put dx dt, comma dy dt there or whatever, feel free. Still totally correct, and you can do that. But these are the important things, and then the only thing that is missing from what you need to know about vectors is the speed. But speed, because we're using x of t comma y of t for position, the speed is the same thing that it was for parametric. So what is the speed? Do you remember? Yeah?
It's just the square root of t x dt squared plus dy dt squared.
Good. I'm using prime notation for all of these notes, so this is how I'm going to give it to you, but what you said is correct. This is the speed of the particle. This is all that you need to know about vectors. So let me, after you write this down, let me open up the day 4 notes that are there and just make sure that you understand everything, and they'll have some examples that we can maybe talk about. You ready for me to move on? This is easy, right? Gotta love it. Okay, so this kind of reviews a little bit about what we talked about for parametric. Talks about dy dx being the slope of the tangent line, and the second derivative of y with respect to x dealing with concavity of that curve, whereas x prime of t, which is dx dt, is the rate at which the x coordinate is changing with respect to time, and dy dt is the rate that the y value is changing with respect to time. In terms of dx dt and dy dt being positive or negative, remember my whole analogy was using the Etch-a-Sketch, where dx dt positive means that the particle is moving to the right, dx dt negative means the particle is moving to the left, dy dt positive means that it's moving up, dy dt negative means that it's moving down. And you could find where dx dt and dy dt are both positive, because for those the particle is moving to the right and up, right? If you had a curve, or if you had the parametric equations, then you could just find intervals where dx dt is positive and find intervals where dy dt is positive and see where they intersect, right?